Hello everyone, this is Alex Rodriguez, your Lifeline leader, and today we're going to be discussing basic chemistry. But first, let's go over a couple of reminders. The profile picture assignment is due this January 23rd at 11:59, and the week 2 homework will be due on January 30th at 11:59 p.m. You will find everything that is due under week 2 Lifeline module on Canvas. We're going to start by discussing the biological hierarchy, also known as the hierarchy of life. You will notice in this diagram that we're going from the very small to the larger things in life that we know most about. We're gonna start with small molecules. However, before small molecules, you have to know that we have atoms, which are what make these small molecules. The example here is a molecule of water, which is made up of three atoms, which are smaller than small molecules. And even smaller than atoms themselves, we're going to be discussing a little bit later about subatomic particles. But moving on from small molecules to larger molecules, which include something like proteins, carbohydrates, lipids, those are the larger molecules. Then we go into cells, which are made up of large molecules. These cells, there we have two main types, animal cell and the plant cell if we're talking about eukaryotic organisms, which we will be talking about mostly in biological principles, but know that there are other types of cells like bacteria as well. We have these followed by tissues, which are a collection of cells that serve a same purpose. For example, here we're talking about cardiac and heart tissue, and here we're talking about leaf tissues. Now we have organs, which are made of tissues. Then these organs, collections of organs, make organ systems, and collections of organ systems make complex organisms like ourselves. Matter. The universe is mainly made up of matter and energy. There are only two characteristics that something needs to have in order to be considered matter. If it occupies space and it has mass, it is matter. And when you think about it, this basically means that everything you can think about is matter itself. Because these are two simple characteristics, very easy to accomplish. It is harder to picture something that is not matter than something that is matter. Now, the atom is the smallest unit of matter that still retains the properties of an element. Atoms consist of subatomic particles, which include protons, electrons, and neutrons. These are the particles that I was talking about before, that are even smaller than atoms themselves. The first diagram that we saw started with small molecules made up of a few atoms, and then now we're gonna see what atoms themselves are made of. Here we have a depiction of an atom. Of course, it doesn't really look like this in real life. It is very hard to see what they actually look like, but this is a very nice depiction to show what it's composed of. The atom is made of a nucleus that has both protons and neutrons in it, and then it's surrounded by electrons. These are the three types of subatomic particles: the proton, the neutron, and the electron. There are other, even smaller pieces, like nucleons and quarks, that we honestly do not have to worry about in this class and probably for your whole college career, because I myself have never encountered any problems with nucleons and quarks. But for the ones that you do need to know, the proton, the neutron, and the electron, these are the characteristics that you have to focus on. There is charge, there is mass, and there is location. The charge of a proton is considered to be positive, while its mass is considered to be 1 AMU. AMU stands for atomic mass units. Protons and neutrons are small, but still in an amount that can be measured. And for that, uh, we have this unit, the atomic mass unit. However, if you look at an electron which does have a negative charge, and we look at mass, it is negligible. That means that it is so small that it barely contributes to the mass of a whole atom, and therefore there is no unit for the mass of an electron. I believe, I remember actually that it's about 2,500 or so electrons that would make up the mass of a single proton. And therefore, you can imagine how electrons contribute negligibly to the mass of an atom. And then we have the location. As I mentioned before, the nucleus has both protons and neutrons in them, while the electrons will be found in the orbitals that surround the nucleus. We're gonna talk about orbitals in a little bit. But the last thing that I want to show here is the charge of a neutron, which, as the name implies, it's neutral. What is an element? An element is a substance that cannot be broken down into any other substance by chemical reactions. Now, this can also be interpreted as meaning a substance that is made exclusively of one type of atom and nothing else. We're going to find a list or a table of all available elements in the periodic table. These would be made of a single type of atom. Question: which four elements make up 96% of living matter? This is something that you probably already saw in lecture, but the answer is carbon, hydrogen, oxygen, and nitrogen. These four form a very easy to remember mnemonic device known as CHON. Dr. Brooks actually has a different mnemonic device, which is a sponge. It's only adding the elements of sulfur and phosphorus to the mix. And as so, you can see how it changes from 96% to 98%. The fact of the matter is that CHON, or carbon, hydrogen, oxygen, and nitrogen, make most of living matter in this planet. The periodic table. All elements have their own symbol, and it is derived from Latin, okay? Which is why not all of them are going to be that easy to remember. But when you see it often enough, it comes to you. These are easy. Carbon is C, helium is He, oxygen is O. Those are easy to remember. Sulfur is also easy, it's just an S. But what is the symbol for potassium? That one is not as easy. That one is K. There's not a K anywhere in the word potassium, but this is because it comes from Latin. We will just have to make do with it and remember it as it is. Potassium is K in the periodic table. Which element is represented by F? This is another easy one. Fluorine. Atomic number. Atomic number equals the number of protons in the nucleus. Oxygen has 8 protons, while carbon has 6 protons. The atomic number is unique per element. Now, this is very important to know because it is actually the number of protons that an atom has that makes it part of that element. You cannot have an atom of oxygen, for example, with 9 protons. That just doesn't exist. If you go to 9 protons, it is not oxygen anymore. It becomes something else. In that case, it becomes fluorine. You cannot have an atom of carbon with 8 protons, for example, because if it has 8 protons, it is not carbon anymore. It would be oxygen instead. So that is the one thing that cannot change from an atom, with it remaining that same kind of atom, if that makes sense. You can change the number of neutrons, And you can change the number of electrons, but you cannot change the number of protons in the atom. So, unless otherwise stated, atoms are electronically or electrically neutral, and therefore that means that the number of electrons also equals the number of protons. Remember, protons are positive, electrons are negative. Therefore, in order to balance out the charges, you have to have equal number of electrons as you have protons. In the case of oxygen, we have 8 protons as the atomic number indicates. So how many electrons would we expect oxygen to have? 8 as well. That way you have 8 positives and 8 negatives, and that comes down to 0. Same with carbon. Carbon has 6 protons, and we would expect it to have 6 neutrons as well. So let's see if you were paying attention. What is the atomic number of hydrogen? We have it right here. The answer would be 1. What is the atomic number of neon? It's always this little number here, 10. What is the atomic, how many protons are in sodium? It's easy. It's also the same number as the atomic number, 11 in this case. How many protons are in zinc? 30, because 30 is the atomic number. How many electrons are in lithium? The answer is also the atomic number, 3, unless otherwise stated, which does happen. How many electrons are in silicon? Unless otherwise stated, 14 is the answer. Periodic table. Elements are arranged in order of increasing atomic number, from left to right and from top to bottom. That means that we go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth, from left to right, and it increases from top to bottom. Atomic mass. The atomic mass equals the number of protons plus the number of neutrons. Remember, we are not going to include electrons in this equation because the mass of an electron is again negligible. It is way too small to be calculated. Why is the mass of the electron not included there? Exactly for what I just said, because the electrons are so small, their contribution to the total mass is negligible. That should be easy to remember. We are never going to have enough electrons in a single atom for it to even amount to the mass of a single proton. And therefore, it's just easier to not count their mass. How would you find the number of neutrons? Now, this is basic algebra if you think about it. The atomic mass equals the number of protons plus the number of neutrons. So if we want to find the number of neutrons, we can simply subtract the number of protons from the atomic mass. And therefore, the number of neutrons equals atomic mass minus the number of protons. In this example here, we have a carbon atom. A carbon atom has 6 protons and it has 6 neutrons, which equals an atomic mass of 12. Now, do not be confused. This is a mere coincidence that the number of protons equals the number of neutrons here. You should not look at the atomic number of an element and say that it automatically has that same number of neutrons. This is why we're giving you a formula. We are going to see other examples where the number of neutrons is larger than the number of protons. So let's see if you got this. We have oxygen here, which has 16 for atomic mass. We can very well approximate this to 16. And by subtracting the number of protons, which is represented by the atomic number 8, we get to the answer that oxygen has 8 neutrons. In the case of carbon, again, we have an atomic mass of 12, atomic number of 6, and therefore we have 6 neutrons. Question: what is the atomic mass of hydrogen? The atomic mass is this number here to the bottom. So we have 1. Or you can say 1.008. Now I'm going to clear the air already about what these decimals mean. And let me begin by just saying that these decimals do not represent the electrons in an atom. Okay, that is not the reason for the decimal number here. Uh, the decimal number is a representation or acknowledgement, really, that there are isotopes out there. Now, I am not going to get into isotopes today because it is not so important for biological principles. However, you are most likely going to take general chemistry at some point, or you have already taken it, and then you already know what these are. But otherwise, we are not going to get into it. Just know that the decimal number is an acknowledgement of isotopes. And that's all I'm going to say. I will happily answer more questions about this in office hours if you're curious, but I am not going to get into it today. Remember, the number of neutrons equals the atomic mass minus the number of protons. How many neutrons are in hydrogen? Then we see that there are 0 neutrons. We wouldn't say that there are 0.008 neutrons, okay? Now we will talk about orbitals. Orbitals are the three-dimensional space where an electron is found 90% of the time. No more than 2 electrons can occupy the same orbital at one time. Now, this 90% requires a little bit of explanation, so let me just say the following. We, at least as of now, in science, we are unable to tell where an electron is at any given point in time. We cannot tell where it is. Electrons are too small and too fast for us to be able to say, okay, the electron is here in right this second. We cannot do that. But what we can do is know where that electron is going to be most of the time, and that is 90% of the time. That is what an orbital is. And each of these orbitals is able to handle 2 electrons at the same time, no more than that. If you put in more than that, it's going to go into another orbital. We will get more into that in just a second, but just know that we are unable to tell where an electron is at all times. Energy levels. The different states of potential energy that electrons have in an atom are called energy levels, or electron shells. Chemical behavior of an atom is determined by the distribution of electrons in the atom's electron shells. Now, all I want you to get from this is that we have up to 4. Actually, we have even more for bigger elements, but uh, we have here in this depiction we have 4 energy levels, and the trend is that the closer you are to the nucleus, the less energy you have. The further away you go from the nucleus, the more energy those electrons have. So the first shell, which is closest to the nucleus, has electrons in this shell that are the lowest energy. Electrons in the second shell have more energy. Electrons in the third shell have more energy still, and so on and so forth. As electrons are added, they tend to occupy the lowest available shell first. So this is the trend that you see. The closer you go to the nucleus, the less energy. The further away you go from the nucleus, the more energy those electrons have. Now, this makes sense if you think about it. What is the charge of an electron again? An electron is negative. What is the charge of a proton? Positive. Now, all of these protons are going to be in the nucleus. Now, if you picture it, a negative electron that is going to be moving closer to the nucleus is going to be closer to that positive charge in the nucleus. And therefore, that electron is going to be stabilized by the positive charge are in the nucleus. But if you take it further away, then the capacity of the nucleus to reach that electron is diminished, and therefore the electron itself has more energy. First electron shell. Only one orbital exists in the first electron shell. And we said before that one orbital is able to handle two electrons at one time. The orbital that we see in the first electron shell is the s orbital. The second electron shell has up to 4 orbitals, and again, each orbital is able to handle 2 electrons at one time. So we have a maximum of 8 electrons in the second shell. Now these are the 4 types of orbitals that we have in the second electron shell. We have the s orbital, the px orbital, the py orbital, and the pz orbital. Now, this is not so important for biological principles, but it's a good thing to know, okay? Those orbitals that look like a sphere are what we know as s orbitals. And those that look like a kind of twisted balloon, if you will, or like a dumbbell, are the p orbitals. And we have 3 of those. We have the px, we would have another one in the py, and we would have another one in the pz. And please remember that no more than 2 electrons can occupy the same orbital. Energy levels. The diagram depicted here are Bohr model representations. That is just another way to depict atoms. Remember, it is not so friendly, if you will, to look at an atom in its natural form. There is not much we can tell from it, but these diagrams give us some information. The information that we get from these is the orbital configuration, basically. We get to see in which orbital these diagrams are, and we get to see the energy levels, which is very convenient. In the example of helium, we have a maximum of 2 electrons in the first shell, and we have 2 electrons in total. For neon, which is the second noble gas, we have a total of 10 electrons. We have the first energy shell full, and then we have the second energy shell full as well, with 8 electrons. Electron configuration of an atom is the particular distribution of electrons among the available shells. For example, oxygen has 8 electrons. Now, this is how we would write the electron configuration of oxygen. First, we have to fill the lower shell. In that case, we're talking about energy level 1. What is the only orbital in energy level 1? It's the orbital s. So we go with 2 electrons there. So now we have 2 out of the 8 electrons that we need to complete oxygen. Then we go to the second energy level, 2. And the first orbital that's going to get full is going to be the s orbital. So we go 1 and we go 2. Now for p, it's a little bit different. Now we have 4 electrons that we have to place in these 3 orbitals. Now the rule is that each one of these has to get 1 electron before anyone gets 2. So what does that mean? That means that the 4 remaining electrons are going to fill the orbitals as follows. 1 for px, 1 for py, 1 for pz, and now we can put 2 in 1. This would go in x. Now we have 2 in px. Now, if we were talking about fluorine, for example, we would add another electron to y, and that would be fluorine. And if we add another electron to Pz, we would be at neon with 10 electrons. And this is how you write that configuration. 1s2, 2s2, 2px2, 2py1, 2pz1. A compound is a substance consisting of 2 or more elements, and it's combined in a fixed ratio. Example of this is water. The chemical formula for water is H2O. We have another example here. Sodium chloride. This is the chemical formula of table salt, the salt that we put in our food. Then we have glucose. C6H12O6. Now, that is a little bit more complicated of a formula, but it is basically just sugar, the sugar that we use in our food, or the glucose that plants use. It is all the same. In these compounds, what do the subscripts indicate? So it is a very easy guess because we have a picture of the water molecule here and we have H2O here. That only the subscript only means that that water molecule has two hydrogens and one oxygen. In the case of glucose, that means that glucose has 6 carbons, 12 hydrogens, and 6 oxygens. That's all the subscript means. If there is no number, there is only one atom present. As you can see in sodium chloride. Sodium chloride is composed of one sodium atom and one chloride atom. Or chlorine atom, sorry. Now, that's basically all we have for basic chemistry. But let's do a couple of review questions. Question number 1. Where are the protons and neutrons located in an atom? The answer to this would be in the nucleus, or the center of the atom. Question number 2. What is the maximum number of electrons that an orbital may hold? That should be pretty easy now because there is only one right answer. The answer is 2. 2 electrons per orbital. Question number 3. Which 4 elements make up 96% of living matter? If you remember the mnemonic device CHON, the answer to this is pretty easy. Carbon, hydrogen, oxygen, and nitrogen. Question number 4. Let's fill in the blanks, referring to the nitrogen element. The atomic mass equals what? The atomic mass equals the atomic number plus the number of neutrons. Question number 5. What are the 2 main characteristics of matter? Those were the very easy characteristics to accomplish that pretty much anything you can think of has. If it takes space and it has mass, it is matter. Those are the 2 characteristics. Question number 6. What element is represented by atomic number 16? How many protons, electrons, and neutrons does it have? So let's have a look at it. Atomic number 16. We go down the periodic table. We have 10, 11, 12, 13, 14, 15, 16. Here we have it, 16. That's the atomic number 16. What element is represented? That would be sulfur. Now, it also asks how many protons does sulfur have. So remember, the atomic number is the representation of how many protons that element has. So the answer to how many protons sulfur has is 16. How many electrons would it have? Now, again, unless otherwise stated, the number of electrons will balance out with the number of protons. So the answer here is also 16. Now, how do we find how many neutrons it has? We take the atomic mass and we can round to 32, and then we can do 32 minus 16 gives you the number of neutrons, and that answer would be 16 neutrons as well. Again, it is only a coincidence that this number of neutrons happens to be the same as the number of protons. Question number 7. What element is represented by atomic number 18? How many neutrons and electrons does it have? So we had 16 here, 17, 18. So 18 is going to be argon. How many neutrons and electrons does it have? Unless otherwise stated, the number of electrons is the same as the number of protons, and therefore we can say it has 18 electrons. Now, for the atomic mass, we finally have an example where the number of neutrons is not the same as the number of protons. We have 18 protons and we have 18 electrons. Now, the equation said that neutrons equals the atomic mass minus the number of protons. The atomic mass of argon can be approximated to 40, and 40 minus 18 is equal to 22 neutrons. Question number 8. Let's draw the Bohr's model for the carbon atom and write its respective electron configuration. This one should be pretty easy given that it only has 6 protons. 6 protons in the nucleus. 6 neutrons in the nucleus as well. 2 electrons go in the first shell. This is the first shell right here, number 1. And the one orbital that we have in the first shell is orbital s. And then we have 4 electrons that have to go in the second shell in order to make up to the 6 electrons. So in the second shell, we would have orbital s. In this case, this is the blue electrons. We would have px, we would have py, and we would have pz over here. But pz, it doesn't even get anything because we don't have enough electrons. And therefore, we give 1 and 1 to 2s. We give 1 to 2px, and we give 1 to 2py. And this is how you write it. 1s2, 2s2, 2px1, only 1 in px, and 2py1, only 1 electron in py. Question number 9. Draw the Bohr's model for the fluorine atom and write its respective electron configuration. Another similar problem. Here we have it. We have 9 protons to work with. So 9 protons also implies 9 electrons. And this is how we're going to do the electron configuration. So first, the first energy gets filled. How many electrons can the first energy hold? 2, because it can only hold 1 orbital. So 9 protons in the nucleus, 9 neutrons in the nucleus, and 9 electrons surrounding the nucleus. But how are we going to arrange the electrons? First, the first energy gets full. So we give 2 electrons to 1s. Then the second energy begins to get full. But first, we have to fill in the s orbital. So 1 and 2 for 2s. And then we have to give 1 to every p before any one of the p's gets 2. That is the rule. So 2px2. Actually, let's go in order. Let's pretend that these are not full already. We can say 1 to 2px, 1 to 2py, 1 to 2pz. And then, and then 1 to 2pc. And then we can go around one more time. We give another to 2px, we give another to 2py, and we ran out of electrons. We cannot give any more. If we had one more to give, we would put it in 2pc, and this would no longer be fluorine. Actually, it could still be fluorine because remember, it is the number of protons that determines the element, not the number of electrons. I take that back. So just understand what I'm saying here. The number of electrons can change without the element changing itself. But if we change the atomic number to 10, for example, then this would no longer be fluorine. We could add another electron here, and that would still be fluorine. So before we finish, I just want to go over a couple of reminders again. The profile picture assignment is due this January 23rd at 11:59 p.m. and the week 2 homework is due on January 30th at 11:59 p.m. Thank you and have a good day.